Hello everyone! Welcome to an exciting journey into the realm of artificial intelligence. Today we're diving into the fascinating world of machine learning, a field that's rapidly transforming how we interact with technology and the world around us. At its core, it's all about teaching computers to learn, enabling them to make decisions and predictions without being explicitly programmed for every single scenario. It's about mimicking the human learning process, where computers analyze vast amounts of information, identify patterns, and then apply that knowledge to new, unseen data, just like we do. One of the coolest and most fundamental parts of machine learning is regression, a powerful statistical tool for making predictions and understanding relationships between different variables. Regression provides us with a framework for forecasting future outcomes and uncovering hidden connections within data, making it an invaluable asset in various fields. Imagine trying to guess how tall a plant will grow, a seemingly simple question with surprisingly complex underlying factors. Regression allows us to estimate the plant's height based on various inputs, such as how much water it receives, the amount of sunlight it's exposed to, and the type of soil it's planted in. At its heart, regression helps us find relationships between things, quantifying the strength and direction of these connections. By understanding these relationships, we can build models that allow us to predict the future with a certain degree of accuracy, enabling us to make informed decisions and plan for what's to come. Think of it as connecting the dots, where each dot represents a piece of information or a data point. For example, you have data, like the number of hours students studied for a test and their corresponding test scores. Each student's data point, representing their study hours and test score, is a dot on a graph, creating a visual representation of the data. Regression then draws a line that best fits those dots, capturing the overall trend and relationship between study hours and test scores. With that line, we can predict a new student's score, even if we don't have their actual test result yet. This prediction is based solely on their reported study hours, leveraging the relationship learned from the existing data. However, it's important to remember that this isn't magic or some form of supernatural ability. It's simply math in action, using statistical principles to uncover patterns and make informed estimations. Scientists across various disciplines, businesses seeking to optimize their operations, and doctors striving to improve patient outcomes all use regression techniques to make predictions and gain valuable insights. The core idea behind regression is elegantly simple. Use what we know, the features or independent variables, to predict what we don't know, the target or dependent variable. In the student example, the number of hours studied is the feature, the input that we use to make our prediction, and the test score is the target, the output that we're trying to predict. Today, we'll explore different regression models, each with its own strengths and weaknesses, and suited for different types of data and prediction tasks. We'll journey from simple linear regression models, which draw straight lines through the data, to more complex tools that can capture nonlinear relationships and intricate patterns. We'll delve into how these models work under the hood, understanding the mathematical principles that drive their predictions. We'll also discuss when to use them, exploring various scenarios and use cases where each model shines. And finally, we'll learn how to judge their predictions using various metrics to assess the accuracy and reliability of our regression models. So, buckle up and let's get started on this exciting exploration of regression and the power of prediction. Let's dive right in with a true superstar of the machine learning world, linear regression. It's a fundamental algorithm, and understanding it is key to unlocking more complex models down the line. We'll explore what makes it so powerful and why it's often the first tool data scientists reach for. The term linear simply refers to a straight line. It's all about finding that straight line relationship within your data. This simplicity is what makes it so elegant and easy to interpret. At its core, linear regression assumes a straight line relationship between the variable you're measuring and the variable you're trying to predict. This means we're looking for a direct proportional connection between the two. A classic example is the relationship between temperature and ice cream sales. Generally, hotter days tend to lead to higher ice cream sales. There's a clear positive correlation. We can represent this relationship visually as a straight line plotted on a graph. This line aims to capture the overall trend in the data. Another common application is predicting house prices based on various factors. For instance, it's a well-known fact that bigger houses usually command higher prices. This is another example of a positive correlation that linear regression can model. To build our model, we first need to collect data. In this case, we'd gather information on the size and corresponding prices of various houses in a given area. Then we plot this data on a graph. Each individual house becomes a single dot, representing its size and price. Linear regression then steps in to draw the line of best fit through those scattered dots. This line represents the model's attempt to capture the underlying relationship between size and price. The mathematical representation of this line is expressed by the formula y = mx plus b. This simple equation is the heart of linear regression. In our house price example, y represents the predicted price of the house and x represents its size. These are the variables we're working with. The m in the equation represents the slope of the line, indicating how much the price changes for each unit increase in size. And b is the y-intercept, representing the estimated starting price, or the price of a house with zero size. Once we have this line, predicting the price of a new house becomes remarkably easy. You simply find the house's size on the x-axis of the graph, trace a line vertically up to the regression line, and then read the corresponding price off the y-axis. In essence, we're leveraging patterns observed in historical data to make predictions about new unseen data points. This is the core principle behind many machine learning algorithms. Linear regression is not only elegant in its simplicity, but also surprisingly powerful in its ability to model real-world relationships. It serves as a fundamental building block and the foundation for many more advanced machine learning models. Understanding linear regression is crucial for grasping these more complex algorithms. That's why it's the perfect starting point as we embark on our machine learning journey together. It provides a solid base upon which we can build more sophisticated models. It's simple to implement, computationally fast, and relatively easy to understand, making it an ideal tool for both beginners and experienced data scientists alike. But how do we know if the line we've drawn is actually a good fit for the data? Let's explore how we can evaluate the performance of our linear regression model. Onward! We've drawn our line, carefully plotting it through the data points on our scatter plot. It seems to capture the general trend, but a crucial question remains. But how do we know it's the best fit? Is this line truly the most accurate representation of the relationship between our variables? Or could there be a better one lurking just out of sight? How can we be sure that we've minimized the error and maximized the explanatory power of our model? Enter least squares, a powerful and widely used method for determining the line of best fit in regression analysis. For each data point, representing an observation in our dataset, measure the vertical distance, also known as the residual or error, from the dot to the line. This distance represents the difference between the actual observed value and the value predicted by our regression line. Square each error, so negatives don't cancel positives, ensuring that all errors contribute positively to our overall error calculation. This is a crucial step in preventing underestimation of the total error. Then, add them up for the sum of squared errors, SSE. This gives us a single number that represents the total error of our model. The best line, according to the least squares method, is the one with the smallest SSE. It's the line that minimizes the overall difference between our predictions and the actual data. Another key metric complementing SSE is R-squared, a score from 0 to 1, providing a standardized measure of how well our model fits the data, showing how much of the target's variation is explained by the feature. It essentially tells us what proportion of the changes in our dependent variable can be attributed to changes in our independent variable. An R-squared of 0.85 means 85% of price changes are explained by house size, suggesting a strong relationship between these two variables. Higher R-squared generally means a better fit, indicating that our model is effectively capturing the underlying patterns in the data. SSE tells us total error. The lower the SSE, the better our model is at predicting the target variable. R-squared tells us how well our model explains the data, providing a measure of the model's explanatory power. These numbers help us judge if our model is good or needs improvement, guiding us in refining our model and selecting the most appropriate features. It's all about measuring, carefully quantifying the performance of our model, testing, rigorously evaluating our model's performance on unseen data, and refining, iteratively improving our model based on the insights gained from our analysis. Science in action, the scientific method applied to the world of data. With these tools, we can build and evaluate regression models confidently, knowing that we have a solid foundation for making data-driven decisions. Let's move to questions with yes/no answers. We'll now explore a different type of prediction problem. Next up, logistic regression, a powerful technique for predicting binary outcomes. What if we want to predict a yes or no answer, like pass, fail, or spam, not spam? Linear regression doesn't work for this. It can give impossible predictions. Enter logistic regression. It predicts probabilities between 0 and 1. For example, it might say there's a 90% chance a student will pass. It uses an S-shaped curve, the sigmoid function, to turn any input into a probability. Low values mean probability near 0, high values near 1. We set a threshold, usually 0.5, to decide yes or no. Logistic regression is perfect for binary classification problems. It's a different shape for a different kind of question. Now, what if our data isn't a straight line? Linear regression assumes straight lines, but real-world data is often curvy. For example, a car's speed versus fuel efficiency forms a curve, not a line. Polynomial regression models these curves by adding terms like x squared or x cubed. This lets our model bend and fit more complex patterns. For instance, plant growth over time starts slow, speeds up, then slows again. A curve, not a line. Polynomial regression can fit this S-shaped pattern for better predictions. But beware. Too many terms can cause overfitting where the model memorizes noise instead of learning the pattern. The key is balance. Enough complexity to fit the data, but not so much that we lose generalization. Polynomial regression is powerful for nonlinear relationships. Use it wisely. Next, let's see how to keep models simple and robust. Enter regularization. When we have lots of features, models can get too complex and overfit. Regularization helps by adding a penalty for complexity, encouraging simplicity. It keeps the model focused on the most important features. Ridge and lasso regression are two popular regularization methods. Both shrink feature coefficients, making the model simpler and more reliable. Ridge keeps all features but reduces their influence. Lasso can eliminate unimportant features entirely. Regularization is about balancing accuracy and simplicity. It's a key tool for building robust, interpretable models. Let's look closer at ridge and lasso. Ridge regression is great when features are correlated, like house size and bedrooms. Standard linear regression can get unstable with correlated features. Ridge adds a penalty based on the square of each coefficient, shrinking them towards 0. This makes the model more stable and less sensitive to noisy features. Ridge never makes coefficients exactly 0, it just reduces their impact. Think of Ridge as a manager who ensures everyone contributes a little. It spreads responsibility across all features, making the model robust. Use Ridge when you believe all features have some value. It's perfect for complex datasets with many interconnected variables. Ridge regression bends the rules, keeping all features in play. It's a smart way to handle multicollinearity. Now, let's meet Lasso, the feature picker. Lasso regression is the master of feature selection. Like Ridge, it adds a penalty, but uses the absolute value of coefficients. This allows Lasso to shrink some coefficients all the way to 0, removing unimportant features. Lasso simplifies models by keeping only the most useful predictors. If you start with 100 features, Lasso can reveal which ones truly matter. It's perfect when you suspect many features are irrelevant. Lasso builds cleaner, more interpretable models. Choose Lasso when you want automatic feature selection. It's a favorite for tackling complex datasets. Now, let's recap what we've learned. We've explored regression models that predict the future from data. Use linear regression for straight-line relationships and continuous predictions. Logistic regression is for yes/no questions. Classification. Polynomial regression fits curves, but beware of overfitting. Ridge regression stabilizes models with many features by shrinking coefficients. Lasso regression simplifies models by removing unimportant features. Each tool has its strengths. Choose based on your data and question. Understanding these models unlocks the power of machine learning. Now go find some data and start predicting.